So hello and welcome to this talk in the LADAL Webinar Series 2022. My name is Martin Schweinberger, and together with Michael Hoare, I'm co-directing LADAL, the Language Technology and Data Analysis Laboratory in the School of Languages and Cultures at the University of Queensland in Australia. LADAL is a school-based support infrastructure for computational humanities or quantitative analysis of language and speech data. LADAL is also part of the Australian text analytics platform, ATAP, which is an open source environment that provides researchers with tools and training for analyzing, processing, and exploring textual data. As such, ATAP aims to provide a powerful, customizable, as well as accessible tool set for a large number of researchers who have or who do not have strong coding skills. Now, before we start, I'd like to read out an acknowledgement of country, which we do here in Australia to express our respect and gratitude towards the Indigenous people of Australia. So I'd like to say that we as members of the University of Queensland acknowledge the traditional owners and their custodianship of the lands from which we are broadcasting this webinar. We pay our respect to their ancestors and their descendants who continue cultural and spiritual connections to country. I'd also like to say that we recognize their valuable contributions to Australian and global society. Now, if you want to know more about LADAL and the resources we provide, please feel free to explore the LADAL website. And no worries if you've missed any of our webinars, all of them are freely available on our LADAL YouTube channel. And you can also find information about past and upcoming presentations in the LADAL Webinar Series 2022 and on the events subpage of the LADAL website. Also, please check out the ATAP website, because LADAL, as I said, is part of ATAP. If you want to keep up with what's going on at LADAL, please feel free to follow us on Twitter or on Facebook. And if you have any questions, suggestions, or feedback, please do not hesitate to reach out by email. So without further ado, it's my pleasure to introduce today's speaker, Dimitrios Vagenas. Dimitrios is a biostatistician and the head of the Research Methods Group at the Queensland University of Technology. He's also the president of the Queensland branch of the Statistical Society of Australia and a member of the accreditation committee of the Statistical Society of Australia. He also holds the highest professional accreditation of the American Statistical Association and the Royal Statistical Society. He has studied animal science, quantitative genetics, and digital biology. His main job is to help researchers do better, and he enjoys better research, and he enjoys working in multidisciplinary teams. So welcome, Dimitrios. I'm very happy that we have you. And I'm very thrilled to listen to your talk. So I'll stop sharing now and I'll hand over to you.
All right, thank you very much for the welcome, Martin. Thank you, everybody. And I hope that this presentation lives up to your expectations. So today we are going to talk about longitudinal data, and I have to, longitudinal data analysis. We've said that the first person who opens the meeting usually does it. I didn't know if it will be done or where Martin will be. So what am I going to cover? First of all, longitudinal data. I'm going to talk a little bit about usual designs for longitudinal data, what makes them different to cross-sectional ones. I will assume that you know a bit about the regression, so that we can get an understanding of the differences between the two. And why linear regression is not appropriate. Now, this part of the talk is something that most people kind of bypass. They don't talk a lot, or they don't get a feeling for, but I think this is the main bit, because once you understand why it's not appropriate, what designs you can have, because they have implications on how you can analyze your data, then the rest are just an advancement. It's not, if you think about it, and if somebody explains it properly, it's not like magic as it sometimes seems. It's just an advancement on something. I'm going to briefly describe the modern ways, as they are called, of dealing with them, and about linear mixed models and generalized estimating equations, more about the linear mixed models. And I have to say it's an advanced issue. I work at the Faculty of Health and I see people from a range of backgrounds. For some of them, it will be relatively easy. The majority of researchers, it's an advanced issue. It is based, I like this book, and I like, I think this is the 2004. There is a later version, but I find the 2004 version, later at the questions, I'll show it to you, I have it over there. It's based on this book, Longitudinal Data. All right. What are longitudinal data? Well, a trivial thing, we need to have 2 or more time points. Otherwise, they are not longitudinal. Either on the same individual or on different ones. In most scientific settings, it's on the same ones. And I'm saying scientific because you can have longitudinal data on other organizations where you don't necessarily have the same people. We'll see one example. You can have fixed or variable intervals between measurements, and you can have experimental or observational design. Again, you can see I'm coming from a health background. You can have a design with an experimental and a control arm, or what we call a cohort study. That's basically what I mean. So the main designs that you can get for longitudinal data are these. You can have multiple cross-sectional data. They are over time, but they are cross-sectional. You will see what I mean. Repeated measures with fixed follow-up, with variable follow-up, and a time to event. You can also have time series. So what I mean by multiple cross-sectional, effectively, you can see on the lines here, you have the ID of the individual. So this is an individual 1. You measured it at 1 and 2. Individual 3, you have them at all 3 times and so on. The point here is that this sample might, at time 1, might or might not be the same as time 2 and time 3. You haven't made any particular effort to sample the same people. They can be, or they can not be. Repeated measures, fixed follow-up, and you will see here an explanation. Units sampled once, so you get your sample, and then the same units, you have them over time, the same individuals over time, and the same time intervals for all units. This is a kind of simple design and can be analyzed with more methods than the variable follow-up. Here, what you have done is, again, you have sampled 4 individuals. You keep the same individuals, but you are not taking measurements at the same time intervals. They can vary. So here we have 4, here we have 3, here we have 2, and so on. Repeated measures, time to event. You have the same individuals. This, nothing finished the study, or something happened, didn't finish the study, and so on. Basically, you are follow them, the same individuals, until the event that you want happens, you are looking at happens, or your study finishes, or you lose them to follow up. And time series, basically you take the same measurement over time, the same measurement. You will see what I mean with examples. So let's see some examples. Multiple cross-sectional, the census. When somebody takes a census of Australia, they don't, the ABS, Australian Bureau of Statistics, they don't try to take the same individuals. They don't care if it's the same individuals. They just want to sample the population of Australia, not sample, record the population of Australia. A lot of individuals will be the same, but it's not by design. It just happens. Fixed follow-up, it's the most intuitive. Every 3 months you take measurements, and it's the most simple. Time to event, the old name was survival analysis. John Snow and the pump, that's how it started in London. But we have to move away a little bit from survival. You can think of it like time to event. A flat tire, that's a time to event. A lamp goes off, that's time to event. something happens, you recover, that could be time to event. If you are recording time and the time when the event happened. Time series, sorry, let's go back. Time series, that's stock exchange. So when you are looking for the price of a stock, that's effectively what you are doing. So all these are the main designs that we have. All right, usually data, when you want to explain something by something else or that something else, different variables, you use a simple linear regression. I assume that you know what a simple linear regression is, but let's go through the assumptions. First assumption, linear model is appropriate. Linear in two respects. You will see a lot of times in books the equation of the straight line. This is analytic geometry. You have x and y axis, you just write a straight line, analytic geometry. The proper assumption is that this P1 applies to all x's. If that wasn't the case, then you will talk about an additive model where this is a function. So it's a linear, this beta 1 applies to all x's. It's a linear function. The residuals are independent of each other. Guess which assumption longitudinal data violate? The residuals have a mean of 0 and a constant variance. You might hear the constant variance as homoscedasticity or heteroscedasticity, with homoscedasticity same variance, heteroscedasticity doesn't have heteroscedasticity, unequal variance. And the residuals follow a normal distribution. So when you have longitudinal data, that's your problem. That's the, and by the way, it's they are in the order of severeness. Let's say departures from this are usually worse than this, which is worse than that one. All right, but why does this matter? That's something that when I give a workshop or a presentation, you ask people, usually they don't know. Well, let's get my weight or my height. You know my weight. Does it tell you anything about future measurements? Well, the answer is yes. If you take my measurement today, weight or height, and you want to know my weight tomorrow, your best bet is what I am today. If I'm 120 kilos, I'm not going to change drastically. I'm not going to fall to 40. So the error or the residual of today, imagine that we have a population, that error, the residual of today, is related to the next measurement. Thus, we have a violation of the assumption. The residuals have to be independent. But why does it matter? Well, our main interest usually is the estimation of means, not variability. Now we are talking about variability. Related measurements will probably have covariance, correlation. Correlation is a standardized covariance, okay? That will affect variability. So what? Well, it's not as simple. If you want to say the average height is 189 meters, there are no problems. There's no problem with that statement. That's the point estimate. Your regression coefficient, let's say, is 189. If you want to say the average height is 189 meters, but with this confidence interval, or anything like that, because remember that confidence interval is linked to the p-value, which is linked to the significance, then you might be wrong if you have used a simple linear regression. You might be. It's not necessary that you will be wrong, but if there is a correlation, because you assume that it's your data are independent or the residuals are independent, it has to be taken into account. You will be wrong. All right, let's unpack this one. This confidence interval is based on an estimate of the residual variance. So you fit in your line and you estimate the distances, the unexplained, and you take the variance of all these residuals, okay? So if there is correlation between the measurements, it has to be taken into account. Let's see it with a simple example. That's for a t-test. We are interested in change over time, and you have measurements 1 and 2, and we define the difference. The difference, delta, is the mean of time 2 minus the mean of time 1, and let's assume these two values for the two means, and the difference is minus 13, simply. All right, furthermore, we assume that the variance at time 1 is 25.2, the variance at time 2 is 58.9. This, yeah, I'm not going to. And we have a standard error of the mean, which is from this formula, you have the standard deviation divided by square root of n, or n minus 1. And for the difference, we have exactly the same. All right. And just in case you are not familiar with what is the standard deviation, is the square root of the variance. It's on the same scale. We use the standard deviation because it's on the same scale as the mean. All right, so we have these things. If we assume independence, the variance, we are trying to calculate the standard error for this quantity. The variance of this quantity is 1 divided by n times the variance at time point 1 plus the variance at time point 2. If we assume that they are related, we have a term over here, minus 2 times the covariance. Okay, so the only difference between the two formulas is that covariance over there. So let's plug in our numbers, and we get a 25.2 plus blah, blah, blah. We do the calculation, and we end up with 1.68. If we assume that they are related, we do the same, but we use a covariance, 15.5, and we end up with 1.06. As you can see, now we take the square root of that. As you can see, you end up with a standard error of 0.18 and a 0.14. This is, again, this is for a t-test. The point I'm trying to make here is that this could be crucial. Okay, it could be a big difference depending on the scale. But if they are related, this is the correct one. This is not the correct one. So why are we interested so much about the standard error? The point estimate is unbiased. The point estimate is correct because it's based on an optimization procedure. There are no, apart from fitting the line, there is no statistics, if you like, involved. It's mathematics, the point estimate. Where the statistics and all the assumptions come into play is for the standard error. This is where the normal distribution, the independence, and homoscedasticity, heteroscedasticity are coming to play. So this is the crucial bit, that you need an appropriate standard error. The regression estimate is unbiased, but the standard error can be biased. Why I'm saying can be? Because if the covariance happen to be 0, then there is no problem. It's a special case. The way I talk to people about that, because they will say, oh, in health, everything is correlated. Well, what I'm eating today, I don't know what I'm going to eat tomorrow. That the correlation there could be 0, for example, but not for other things, height, weight, biological indicators. Probably the words I use, they will be limited and correlated. This is some observations for correlation in longitudinal data. They are mainly for health, but I think they will apply more generally. They are empirical observations. Again, they are from the Fitzmaurice book, and he explains the mechanism on why this could be the case with the true measurement, the error of the measurement, and what you actually measure. And we end up with correlations being usually positive. They often decrease with increasing time separation. My weight today with my weight tomorrow will be probably highly correlated, but my weight today with my weight in 5 years, the correlation will be, and we are talking about a sample from a population, will be lower. Rarely they will go to 0, but rarely they will go to 1. So they will be somewhere in between there. So we are going much faster than I thought. A very brief introduction to analyzing longitudinal data. So this is a regression with 3 time points. Okay, this is actually kind of the regression that you will do with the repeated measures ANOVA. That's how I initially had it. So you have time 1, time 2, and time 3. And all we have done is written them in a matrix form. So y1 equals a1 plus b1, x1, 1, p2 times that, and so on. So you write a simple linear regression with 3 variables, and this is the residual. And the same with time 2, we have the intercept, and so on. So let's look at this part, the residuals, which are the important. We assume multivariate in simple linear regression. We will assume multivariate normality and assume that the same variance applies at each time point, at each regression, and they are independent of each other. So we assume a 0 correlation. That's a simple regression. So in the simple regression, this variance covariance matrix, imagine we have a T1, T2, and T3 here, and T1, T2, T3. They are assumed to be exactly the same variance and a 0 correlation, no covariance. Now, the simplest alternative, which what happens in the repeated measures ANOVA, is that what we call a compound symmetry. So what happens here is we have exactly the same variance, but we assume also that T1 with T2 have the same covariance as T1 and T3. So all the time points have exactly the same covariance. And I'm writing there Fisher pots and plants, the pinch of salt. Why? Up to when mixed models came into play in 1980, I think, or 1980s, somewhere there, end of the 70s, most people were using, as far as I know, repeated measures ANOVA. When we are talking about humans and in health, usually this assumption of the compound symmetry is inappropriate. And that has a historic reason. So here comes Mr. Fisher. Fisher was working in an agricultural station. So they had different fields with different subplots, and they will plant the same varieties in, say, 3 or 4 different fields, and then they will analyze the data. So for Fisher, this made sense to have something like that, because field 1 with field 2 will, on average, have the same correlation as field 1 and field 3. So he could make this, it didn't really matter which 2 plots he picked. On average, they will have the same correlation, and most probably the same variance. So those were tenable assumptions for him, but not for humans, because this can change. As I showed in the previous slide, that's not the case. As we saw here, the correlation can be changing. So this is an inappropriate variance covariance matrix. It will estimate, it's a simplistic way of estimating the standard errors. So with compound symmetry, which is what repeated measures ANOVA makes as an assumption, we assume that the errors have the same variance and covariance. All time points have the same variance. All time points have the same covariance, and I explained it there. And are these tenable assumptions? In most cases, not. That is not very satisfactory. All right, let's move to linear mixed models. Linear mixed models distinguish between fixed and random effects. And those fixed and random effects are something that people have big problems when they start on understanding what's a fixed and what's a random effect. Well, a fixed effect, you can treat something as a fixed effect as when the variables for which the only levels are under consideration, the only levels under consideration are contained in the coding of those effects. What all this says is that everything that I want to know for these variables is contained on the data that I have gathered. We'll see examples. A simple linear regression model or a GLM, where you can have not a normal distribution, you can have a logistic, a Poisson, a negative binomial, is a fixed effects only model. Everything that you want to make a statement about is contained on your data. A random effect. Variables for which the levels contained in the coding of those factors are a random sample, that's the important bit, a random sample of the total number of levels in the population for that factor. This might sound very complicated or not intuitive. I'll give you an example. All right, what does this mean? Well, the way I think about it is I'm not interested per se on them, but what they represent as a part of the population. So when you go out here in Brisbane and you want to estimate the height of men in Brisbane, you take 100 individuals, 100 men randomly. Are you interested in those 100 men per se or 100 women? No. You are interested in what they represent as part of the population of men of Brisbane or women of Brisbane. In other words, you could have another sample of 100 men and you will be okay, or another 100 men, and so on. So the participants just happen to be there and they represent part of the population. That's all. And you assume, the further assumption you make is that they come from a distribution, usually normal, which creates that you treat them as kind of as random variables in statistics. So you assume that they come from a distribution, a population with a distribution, and that then how it's treated in the model and how it's analyzed in the black box, which you don't see at the computer, creates a correlation between the levels of the random effects. And this is what we want. Basically, you are saying these random effects are the things that create the correlation. I believe that these are the things that create the correlation. So I'm not interested per se for them, or on them, or I assume that they are the things that create the normal distribution. Fixed effect examples, if you are interested in genders and you have sampled all the genders that you are interested in, groups, you are interested in Greeks and Australians, you get some men from Greece and Australia. Age, I'm interested only in these genders, groups and ages. Everything that I want is in that one, in my sample. Random effect examples, person, batch, sample. I'm not interested in these particular persons, batches or samples. If you are in a company which produces, say, antigen tests, you are taking batches and you are analyzing them for quality control. You are just interested in what they represent as the general population of samples. Sorry, I'm looking at the time as well. And I believe that there might be a correlation between measurements taken on these persons, batches, and samples. That's why when you have the same person over time, you put that ID usually of the person as the random effect. I'm saying that these people, the fact that these measurements are taken on the same individual will create the correlation. A bit of nomenclature. Now, I'm dealing in my everyday work with people from different disciplines. And what I have found is that different disciplines will might use a different term for the same thing. So a mixed model can come with different names in different disciplines. Mixed model, hierarchical model, multi-level model. Usually, they will mean the same thing, but you have to be careful of not assuming that they mean a mixed model, but clarify that they mean a mixed model. Why? Well, what I have found is, for example, with the hierarchical, sometimes they will mean a mixed model, and sometimes they will mean a nested simple regression model. So if you have gender and ethnicity, sometimes they will say, oh, a hierarchical model will be a model without the ethnicity or without the gender. So the proper term for me will be a nested model. I've seen that in some disciplines, and I have to ask, what exactly do you mean by a hierarchical regression? So be aware and be careful. Now, when we talk about multi-level models, remember, they are still mixed models. This goes, we are talking about longitudinal data, but exactly the same can happen with what we call cluster data. And multi-level models or this version of mixed models are better explained in a context of cluster data. So we can have random effects more than one. And we assume here that the variance and the correlation come from different sources, levels, and we want to attribute it to them. We want to partition this variation or correlation. I'll give you an example. It's easier to understand with a classic example of cluster data. We have students in classes and schools and districts and so on. So you can see that there is nesting there. There's a hierarchy of data. So students might have correlated measurements because they are in the same class, because of the same teacher. They are in the same school. The school two different schools might have different ways of teaching students. They could be from in the same or different districts and so on. What you do with a multi-level, and those are nested, not crossed, for those who might have seen this. A class is in a school, which is, sorry, this is a mistake. I wanted to say classes in a school, which is in a district, and so on. So what we will do then is we will say, all right, level 1 is the class, level 2 is the school, level 3 is the district, and we will fit these as nested random effects, and we will try to partition these variance, covariance into these components. A parenthesis here, I personally came across this for the first time in a quantitative genetics setup, where quantitative geneticists are a little bit different from everybody else. Everybody else sees that variance, covariance, the correlation as a nuisance that has to be taken into account. In animal breeding quantitative genetics, that bit is important because they will estimate heritabilities, genotypic and phenotypic correlations from a mixed model using something like that. Anyway, the bottom line here is that we have different levels, and that's why those are random effects, and we are trying to partition the variation into these different levels, and they are called multi-level models. Now, if we put fixed and random effects together in a model, we have a mixed effects model. And as I said, a linear regression is a fixed effects model. That's important for those who are doing model selection. One thing you can do is test if you need a mixed model by fitting the simple linear regression or the simple model, the fixed effects model, and then add the random effect and test if these two models are significantly different. Mixed models were developed first to deal with correlated Gaussian data, normally distributed data. And the correlation between the observations is due to the random effects. That's like a summary. They can also handle non-normal data as well. The advantages of the mixed models, read that one compared to repeated measures ANOVA. They can allow random effects to be specified and computed and partition this variation and this correlation. They can allow correlation of errors. They can allow error terms to exhibit non-constant variability. They can account for heteroscedasticity. And they can handle missing data, whereas older procedures, repeated measures ANOVA or regression, they cannot handle missing data properly. They just delete. If you have one a missing measurement out of the 3, you're gone. Generalized estimating equations. The basic difference between mixed models and generalized estimating equations is really in the estimation procedure, in the black box that we don't see. They use, you can only specify one grouping factor. They use what we call generalized estimating equations. So they are not using maximum likelihood. They are using another optimization procedure, which has very good properties for longitudinal and cluster data. You can only specify one grouping factor. They truly, these ones, they are not interested in partitioning variation or seeing where it comes from. I just want to take it into account. Give me the level which you think is the most appropriate. And you go, all right, participant ID, take that correlation into account, adjust your estimate, and that's it. Does not make any distributional assumption. Now, this is the robust estimator, or it's like I say to people, the magic property where you can misspecify the distribution and it will arrive to the correct result, but it comes at a cost. It comes at a cost with wider confidence intervals, and sometimes I've read about biases. So keep it in mind, it's worth trying to fit the correct distribution, because there was a period where people would go, yeah, they have this robust estimate, sandwich estimator, robust estimator property. They will arrive to the correct conclusion. Well, they are not as efficient to start with, even if they arrive. And sometimes I think it can result in biases. You don't need to define fixed or random effects. So for beginners, I will say it's easier, because the mixed models have, you need to think about your random effects. All right. What is the difference between the two? They will not give you exactly the same. The basic difference is how the estimate happens. Now, one thing that and that's this point over here, one thing that I will say is the mixed models are for individual predictions. The GEs are for the mean of the population. Now, if the data, let's start with that. If the data are normally distributed or symmetrically distributed and you have specified it properly, they will arrive to the same answer. It doesn't really matter. If it's not normal or symmetrically distributed, like a logistic regression, they will not give you the same answer. And the mixed models, think of it like they are good for predictions for the individual, whereas a GE it's good for the prediction of the average of the population. So if you want to find out, if you go to the GP and you say, all right, I want you to estimate, because they have a little program, what's my chance of getting a heart attack? And then he should use a mixed model, because it's a prediction for you, for reasons that we haven't touched here, but it's a prediction for you. If you're an epidemiologist and you say, all right, I'm going to do this intervention, what will be the effect for the population? They should use a GE. Again, if the data are not symmetrical, it's good to know what you're doing. That's the main difference. And sometimes, a lot of times, people don't know what's the difference. Sorry about that. Covariance structure. Now, as I said, the mixed models at I didn't say it, but the mixed models, when you define the random effects, effectively, it's an unstructured variance-covariance matrix. Just keep this in your mind. For the Gs, you need to specify that covariance structure, and you have various choices. And yeah, again, the sandwich estimator, yes, they will most probably arrive to the same conclusion. They have other subtle differences, but we are not going to go into them. Again, I repeat, if they are normally distributed, they will give the same result, or symmetrically distributed. So that's the end, and that was very good time for 100 slides. Sorry. I hope you have found this productive and I haven't been rushing through. And I'll give you 3 references that I think are very good. The Fritz-Maurer et al. 2004, it's very good for the theory. The Zur et al., the mixed effects models and extension in ecology with that, it's an all-rounder book. I really like it. It has penguins on the, I call it the penguin book. It's about ecology and it has penguins on the cover. It's a very good book and you can learn R with that if you are not using R. The West et al. Linear mixed models, a practical guide using statistical software. I don't know all statistical software. What he does is he fits the same model with, I'm pretty sure with these 5 software. And this is great because I speak R, I speak say SAS and SPSS. I don't know HML or Stata. And people will ask me, oh, how can I fit this model, this mixed model? I'll go, I don't know, but I'll tell you, I'll find out. I'll go to this book, find an appropriate model in R where I know what it means. And then I'll find the code that he has for state and I'll go, here you are. That's how you do it. Just change your variables to his variables. And this is me.